In this video, we will take a brief look at scalar and vector quantities. We'll state exactly what a scalar quantity is, what a vector quantity is. We'll give examples of each, and of course we'll give comparisons between scalar and vector quantities, which of course are related. Now let's take a look at scalar and vector quantities. Now, what exactly is a scalar quantity and what exactly is a vector quantity? A scalar quantity is one which has only magnitude or size, whereas a vector quantity has both magnitude and direction. So, scalar quantity and vector quantity. Right? So we say that a scalar quantity has magnitude or size only, whereas a vector quantity has both magnitude and direction. Right? So a scalar quantity is one which has magnitude or size only, whereas a vector quantity has both magnitude and direction. Now let's look at a few examples of scalar quantities and vector quantities. Examples of scalar quantities include length, mass, time, density, and pressure. Look at another, energy. Energy is also a scalar quantity. Now let's look at some examples of vector quantities. Examples of vector quantities include displacement, velocity, acceleration, momentum. Right? So we listed a few scalar quantities and a few vector quantities, and of course these lists are not exhaustive. As we go deeper into the course, we'll be introduced to additional quantities, some of which will be scalar quantities and some of which of course will be vector quantities. All right? Now let's look at a particular comparison of scalar and vector quantities, and for this comparison we will look briefly at distance versus displacement. So we're going to look briefly at distance versus displacement. Right? So we'll define each term and we'll then go deeper into the comparison, right? So what exactly is distance? Distance is defined as the path length between 2 points. So distance is the path length between 2 points, right? If you walk a certain path between 2 points, then the length of that path will give the distance traveled. Distance is a scalar quantity. So distance is a scalar quantity. And of course, being a scalar quantity, it means that it has magnitude or size, but no direction, right? Now let's talk about displacement. So this is distance. Let's talk about displacement. Displacement is the distance moved in a specific direction. Right? So distance is the path length between 2 points, whereas displacement is defined as the distance moved in a specific or in a specified direction. Now, since of course direction is mentioned, then it therefore follows that displacement is a vector quantity. Right? So displacement is a vector quantity. Now, to illustrate the difference between the two, let's look at a case of traveling a path. Now, let's say an individual walks from point A to point B along a path that looks like this, right? So the person travels from point A to point B along a path, along this path, right? In that direction, right? Now, the distance traveled would be equal to the length of the curved path AB. So if this person wanted to know the distance he traveled, then he could basically measure the length of the curved path AB, because he would have walked along that exact path, and therefore the length of that curved path would have given the distance traveled, right? However, suppose they wanted to find the displacement, the person's displacement. The displacement, however, would be the length of the straight line AB. And to just show that, the displacement would be the length of the straight line AB. So if you draw a straight line from A to B, then the length of that line would represent is displacement. So the displacement would be equal to the length of the straight line AB. Right? Now let's momentarily assign some values to these. Let's say, for instance, the length of this curved path was, say, 25 meters. Then it would mean that the distance traveled is equal to 25 meters. And let's say the length of the straight line was actually 15 meters. We would say that displacement is equal to 15 meters. But is that statement complete? No. So far, we've only stated the magnitude of the displacement. Because displacement is a vector quantity, we must also state its direction. So because a person walked from A to B, then we could say 15 meters in the direction of AB, or from A to B. Alright, so we could say 15 meters from A to B, or we could say 15 meters in the direction of B, so that we know what direction the person would have taken. Right? So here we basically looked at a brief example or a brief comparison between distance and displacement. We said that this person walked along a curved path AB. The distance traveled would be equal to the length of the curved path AB, whereas the displacement is the length of the straight line AB. And if, for instance, the distance traveled or the length of the curved path AB was 25 meters, then that would have been the distance traveled. If the length of the straight line AB is 15 meters, it is not just sufficient to give displacement as 15 meters, because displacement, being a vector quantity, must not only have magnitude but direction as well. And so we state the direction as from A to B, or we could have said in the direction of AB, or in the direction of B. Right? Now let's look at let's continue to look at distance versus displacement, and this time we'll actually show a body moving from point A to B and back to A. We will basically calculate the total distance traveled, and we will also calculate the person's net displacement after returning to point A. So let this be A, and let this be B. And let's say those 2 points are separated by a distance of 20 meters. So the length of part AB is 20 meters, right? So we're going to look at the person is going to walk from A to B and then back from B to A. So we're going to look at, let's say we look at the stage. So we're going to have A to B, B to A, the distance traveled. So distance traveled and also we're going to look at the displacement. And at the end we'll of course look at the total for those 2 stages, right? So we're going to look at the total, or let's call it the total. So if this person is walking from A to B, then the distance traveled would be 20 meters, right? So in walking from A to B, the distance traveled is 20 meters. In walking back from B to A, only thing which has changed is the direction, but the length of the path has not changed, and therefore the distance has not changed, it has remained the same. So therefore the distance traveled back from B to A is also 20 meters. And so if the person walks from A to B and back to A, then the total distance traveled is obtained by simply adding these 2. So this gives us 40 meters, right? Now let's look at the displacement. Now we said that displacement is a vector quantity, and being a vector quantity, displacement not only has magnitude but also direction, right? Now usually when dealing with vectors, if in one direction the vector is treated as being positive, in the exact opposite direction the vector must be treated as being negative. What exactly does that mean? If in walking from A to B the displacement is treated as being positive, in the exact opposite direction the displacement must be treated as being negative. So let's say our initial direction is positive. So in going from A to B, the displacement is plus 20 meters. When the person stops and turns to go back in the opposite direction, then it means the displacement from B to A would be negative because he's now going in the opposite direction, right? And so the displacement from B to A would be minus 20 meters. Now when you add those 2 values, plus 20 minus 20, then this gives us 0. So what do we notice? We notice that the person's distance traveled is 40 meters, but his displacement or his net displacement is 0, right? So we say his net displacement is 0, right? Now, if the body's net displacement is 0, or if the person's net displacement is 0, does this mean that the person did not move? No. What it basically means is that the person would have returned to the exact starting point. And having returned to its exact starting point, the net displacement would be 0, right? So in this example, of course, we looked at a further or continued the comparison of distance versus displacement as a comparison between scalar and vector quantities, right? So we said that basically in going from A to B, distance traveled is 20 meters. In going back from B to A, same distance is traveled, and the total distance traveled for the entire journey, A to B and back, is 40 meters, right? Now distance, of course, is a scalar quantity, so that was relatively straightforward. Displacement, on the other hand, is a vector quantity, and therefore we must take the direction into consideration. So if we treat the initial direction A to B as a positive, then in the opposite direction the displacement must be treated as being negative. So A to B are plus 20 meters for the displacement, B to A minus 20. When we add those 2, we get 0, and so the net displacement, of course, is 0, right? So despite having traveled a total distance of 40 meters, the net displacement, of course, is 0. Now if we look at the other way in which displacement is often defined, we can say that, for instance, displacement is the straight line distance. Displacement is the straight line distance from some reference point. Right? So displacement may often be defined as the straight line distance from some reference point. So if we have a reference point, we can simply measure the straight line distance from that point to any other point, and that will give us a displacement. So in this previous example, the displacement from B to A, our starting point, would of course be our reference point, and so the displacement from A to B is a straight line distance from A to B. Right? Now, having said that, if you look at this, now when the person starts at A, goes to B, and ends up back at A, the net displacement is 0. Now, if you look at this definition, the straight line distance from some reference point, the straight line distance from any point to itself must be 0, and therefore, because this person started at A and ended up right back at A, then the net displacement, of course, is 0. Right? Good. In this other example, we will look at the case of an athlete who covers exactly one lap of a 400-meter track. Right? So let's look at the case of an athlete who covers exactly one lap of a 400-meter track. So let's say this is the starting point A, right? And this the length of this track, of course, is 400 meters. Now, when the athlete finishes a race, he would have covered a distance of 400 meters, right? So it is a 400-meter track, and therefore, if the athlete completes exactly one lap of the 400-meter track, then the distance traveled, of course, is 400 meters, right? So this is a 400-meter track. Now, however, if the athlete completes exactly one lap of the track, then it basically means that he would have ended up right back at his starting point. So that means he starts at A and ends at A, and just as with this situation, his net displacement is equal to 0, right? So we've used this comparison between distance and displacement to show that a body's net displacement being 0 doesn't necessarily mean that the body did not move, right? The body could have moved and traveled a very large distance, but of course, having returned to its starting point, the net displacement, of course, will be 0. Now, to continue our look at scalars versus vectors, or comparison of scalars and vectors, we'll do one other comparison, and we'll look at speed versus velocity. Speed versus velocity. All right? So, as before, we'll give a brief definition of each of those two terms, and we'll look at examples and compare them. So speed is defined as the rate of change of distance traveled with time. All right? So speed is the rate of change of distance traveled with time. In some books, you may see just the rate of change of distance, because by saying rate of change, they imply with time. But of course, if you see with time, it doesn't make it wrong. So speed is the rate of change of distance traveled with time. And to calculate speed or average speed, so we say average speed is equal to distance traveled over time taken. So average speed equals distance traveled over time taken. And of course, we know that speed is a scalar quantity, right? So speed is a scalar. Now, if we recall information from the situations we looked at earlier, right? We looked at a situation where a man walked from point A to B and back from B to A. We were able to obtain his total distance traveled as well as his net displacement, right? So in that situation, the total distance traveled was 40 meters, right? Now let's say this was done in a time of, say, 40 seconds. So the time taken is equal to 40 seconds. Now that we have a value for the time taken, we can go ahead and calculate the average speed. And so the average speed is equal to distance traveled divided by time taken. So this gives us 40 meters divided by 40 seconds, which of course gives us 1 meters per second. So the man's average speed, or his speed on average, was 1 meter per second, right? Now, let's also calculate the average speed for the situation involving the athlete who completed exactly 1 lap of the 400-meter track. Now, in this case, of course, the total distance traveled is equal to 400 meters. And let's say this was done in a time of 50 seconds. So the athlete completed 400-meter track in 50 seconds. And so the average speed is equal to distance traveled, 400 meters, divided by time taken, 50 seconds. And so this gives us 8 meters per second, right? So this runner's average speed would be 8 meters per second. Now, during the race, there will be points where the athlete would have been going faster, and there will be times when they would be running slower than 8 meters per second. But this, of course, represents his average speed, right? Now, let's look, of course, at velocity. Velocity is defined as the rate of change of displacement. So it's the rate of change of displacement with time, right? And we calculate average velocity using the formula average velocity equals net displacement divided by time taken, right? And of course, we're dividing net displacement by time taken, and if we make a comparison with speed, as we're doing, then we will know that basically velocity is a vector quantity, right? So velocity is a vector quantity, and as such, it has both magnitude and direction. Now again, because we're making comparisons, we'll of course then calculate the average velocity for each of these situations as well. Now in this situation where the man walked from A to B and back, he traveled a total distance of 40 meters, but of course his net displacement was 0. So in this situation where the man walked from A to B and back to A, his average velocity is equal to its net displacement, which is 0, divided by the time taken, 40 seconds, and this would still give us 0, right? In the case of the athlete who covered exactly 1 lap of the 400-meter track, which means it started and ended at the same point A, his net displacement was also 0, and so his average velocity would be given by net displacement, which once again is 0. This time the time taken is 50 seconds, and so its average velocity is 0, right? So about its average velocity being 0, does that mean the body did not move? No. So the body's average velocity being 0 does not mean that the body did not move. It simply meant that basically the body's net displacement for its journey was 0. In other words, it started off and ended at the exact same point, and as a result, its net displacement and hence its average velocity was equal to 0, right? So generally, regardless of how fast the body was moving, once it basically periodically returns its starting point, it means that every time it does so, its net displacement will be equal to 0, and its average velocity will also be equal to 0, regardless of how fast the body was actually traveling.